All right, so in this video lesson, we are going to study about the chain rule and one direct application of that, the implicit differentiation rule. Okay, so now when it comes to the chain rules, the chain rule is something so important that it's been existing. It exists throughout all the way throughout your calculus 1 classes and all the way throughout your entire progress in studying about calculus until this point right here. And we actually now, for this chain rule, we are going to be studying the much more advanced version of the chain rule. So I'm saying this because what I mean is that you have seen chain rule already been in your work, even if multivariable functions like that earlier. So for example, we have seen functions like that. We have seen problems like this. Say it might have come throughout the examples that you have seen that I deliver throughout the class, or in some other video lectures. But let's say we have a function as following: sine of x, y, for example. And then from this function, obviously being a multivariable function, and then if you are asked to find the partial derivative in respect to x, for example, then there's the outside function, easy to recognize, and then the main variable that we're targeting at is inside of that sine function. So the chain rule here, so when I explain about this example, or at least something similar, I must have mentioned once or twice that we got to use a chain rule. So the chain rule says it's cosine because it's the derivative of the outside, and so keeping everything inside, and then multiply with the derivative of the inside in respect to x right here. So that's why we're looking at the y. Okay? But so now, ladies and gentlemen, this chain rule is the very simple chain rule that we've been using, that the exact same chain rule version from calculus 1, from the differential calculus that we've learned long before this course here. However, the chain rule I'm about to introduce here is a more advanced. It's still the chain rule, but it's a lot more advanced than this. Okay, and so now allow me to erase this quick little reminding example. But now let me promote a different problem right there to illustrate the idea. Okay. So now to study about the more advanced chain rule here that's suitable for the multivariable function, let me start out by giving you an example. A demonstration example over here. Let's say we're starting out with a given function. Let's say a function of 3 variables, okay, x, y, and z. And so this idea works with functions of 2 variables, functions of 3 variables, and when we're now studying about specifically about the chain rule that applies to multivariable functions, then we don't have to focus specifically to 2 variables or 3 variables. So here I'm using a 3 variables example. It's a decently good enough amount of variables involved in the function. Okay, 2 variables I feel a little too little for us. Okay, so this function f of x, y, z, 3 variables in this function. Let's say the function here is x times y plus z. Okay, so that's our function f of x, y, z. And then this function here, I am going to give an additional given information. So now, the idea now is that this function here, each of the variables x, y, and z here is further defined. I'm using the word further defined. So x here is defined as a function in terms of s and t. So x equals s squared. So now x is a function in terms of x and t, of s and t. Even though we don't see t here, but I mean x here is a function of 2 variables, s and t. Even though t is not directly present in this particular definition. Y is s times t. Okay, and now so clearly y is a function of s and t. So just in that argument, I see that x can also be regarded as a function in terms of both s and t. Okay, so like I said, each of the variables here is further a function in terms of s and t. So z is defined equals t squared. Okay, so z equals t squared. So z, even though we don't see the s variable being present in the definition of z variable, but the z can also be regarded as a function of a two-variable function, z of s comma t, and that's the idea. So that's everything about the given information. We have f, starting out with f as a function of x, y, and z being given as x times y plus z. But then each of the x, y, and z has its own definition as a function in terms of s and t. All right, and so now we want to find. So think about it in the long run right here. If we substitute each one of these expressions into the actual function, then we will definitely end up with some function. Or you see, if we substitute s squared for x, s times t for y, and t squared for z right here, then we would end up with a function. And of course, it's going to look different with the original function. So let's call that g. But g here ending up with g of s comma t being equal to f at s squared, comma, because s squared is substituting for x, comma, s times t, comma, t squared. And so what I meant by saying earlier as a final function being g of s and t, because after we substitute it in, we're going to end up with a function in terms of s and t. Okay? Or we can just even say that it's the function f itself, but turned out to be a final function in terms of s and t. We can also retain the same name like that, because it will come out with the same output anyway. Okay, so in that way, yeah, so we expected a final function in terms of s and t if we really gonna substitute those representations into each of the variables here. And so that's why, in that reason, we are asked now, what if we're asked now as our goal, okay? As our goal here, can we obtain the partial derivative in respect to s? All right, and the partial derivative of the function f in respect to t, because s and t are the two final variables involved in our function f. Okay, so since I mentioned about we can easily substitute these expressions for each of the x, y, and t, z into the current function right here, then one route of doing that, I'm just saying one way of doing this, one way of achieving, one way of getting the partial derivative of f in respect to s and partial derivative of f in respect to t, one way of doing that is that we can really go ahead and substitute it in. So I'm going to create f of, I'm going to go ahead and find out, evaluate as f at s squared times st, s squared and then s times t and then t squared. And then the function f itself was x times y. So we have s squared times st, okay, plus, and then z variable is a t squared. So my final function here is a s cubed t plus t squared. So apparently and clearly speaking, this is our f of s comma t right there. Okay, and that's what I was saying. That's what I wrote down earlier about the what we expected to have, a final function in terms of s and t. Okay, and so from this one here we can easily find the following. Okay, df ds. And so now just the usual partial derivative work will come out. Right from this final one right here, I'm looking at 3s squared t. Okay, that's the first term, and then that's it for df ds. And then the partial derivative of f in respect to t can be easily found to be s cubed plus 2t. Okay, s cubed plus 2t. All right, and so in that way, we don't really see anything much, and no one can believe that there's a whole chain rule being hidden behind the scene in every single step. So now my point I'm trying to say is this route of work, I'm not too interested into this route of work. You know, substitute all of the variables expressions into the original function and come up with a final function in terms of s and t, and then finding the partial derivative. Yes, we can do that, but there's a different way of doing that, and it could be faster. Now maybe somebody viewing this video lesson is not very convinced that I'm saying it's going to be faster, but for a more complicated function it will be faster. It will be a lot faster. Okay, so this way, yes, it works. I'm saying it works, but it's not very interested here. Okay, because that's not our goal of, it's not bringing out anything new for us to study. Okay, so I'm going to leave that here. I'm going to roll back to the other board right there. So how about we're going to forget about substituting these expressions into each of the x, y, and z. Let's forget about that. So we just know that it exists somehow. So, and yes, I expect that we will have a final function in terms of s and t. But right from there, without worrying about substituting, okay, we still want to achieve that goal of finding the partial derivative of f in respect to s and the partial derivative of f in respect to t. But so now, at this point right here, I'm about to show you how the chain rule works. Okay, so chain rule, as the way how it's named, it's a rule. So I'll just now get straight into the point, showing you the rule, and then from there we're going to recognize what's in that rule so that you can remember after the lesson is over. Okay, so with this method now, using the chain rule, and along this particular problem, even though I didn't really specifically write down what the chain rule is, right? But we're going to learn that through the problem right here. So df, ds right here. So observe again. In my function, okay, s and t is sort of like the internal variables, the sub-level of variables inside each of these x, y, and z. Okay, so this is my first step right here. I am going to, and this is what we're going to have. I'm going to have a y times 2s, okay? And I'm on my way of finding the df ds. So what I'm saying now is that this partial derivative will equals y times 2s, okay? Plus x times t, okay? And then plus 1 times 0. Because right now I'm telling you. Okay, so of course I understand that you have a lot of questions, but right now I'm just telling you that's how I'm doing it with a slightly different methods right here. And I didn't give out much explanation yet. All of a sudden I'm just throwing at you there's a y times 2s, x times t, and then plus a 1 times 0. And then of course in the next step, and I'm going to leave some good amount of space here. In the next step, see 2s. Now y here is explicitly defined as s times t. So I can bring this and substitute that into my current result there. So y is s times t. So s times t times 2s. Okay, plus, and similarly, x was defined explicitly as s squared. So here I'm looking at s squared times t. Okay, and no one can argue about that. And then all that here is 0. So I don't need to have that final term. So my final answer here comes out being, okay, 2 s squared t plus s squared t. All right, 2s squared t plus s squared t, which adds up becomes 3s squared t. And this is exactly agreeing with the result I've got by using the earlier method, the method that I brought up and then quickly erased away. All right, and then similarly, so I found partial derivative of the function f in terms of s. I'm leaving some good amount of space here. Let's now advance over to finding partial derivative of f in respect to t. Okay, so now again, the scary part here, I'm just going to throw you my step without much explanation, and then eventually I'm going to come back and make you realize what I've done in there. Okay, So this is what I'm going to do. For df dt right here, I'm using the chain rule, and this is what I get. This is the setup that I get right here, according to how I'm using the chain rule right now. All right, so I'm getting y times 0, okay, y times 0 plus x times s, okay, plus 1 times 2t. All right. Again, I mean, I just wrote it down and without giving much explanations in why I got that and why I got that, because I want to save that for, I just want to show you that if you follow with this method that I'm doing right now, if I'm going with a completely different route right here, and I still got the same final answer with the partial derivative in respect to s. And so I should be able to get the exact same answer for the partial derivative in respect to t compared with the methods we've done earlier. So this is now a 0. Doesn't matter what y is, 0. X, now we can bring in the representation for x equals s squared that we've seen from the other board. X equals s squared. Okay. And so that term is 0. We don't need to write it down. So here I'm looking at s squared times s, right, plus 1 times 2t, which is just ridiculously 2t. So all together, this is s cubed plus 2t. And once again, this is now, I call this, this is a completely different route right here. But now I see that I ended up with the exact same answer with how I found that partial derivative of f in respect to t previously with the other earlier methods. All right, so once again, I said that I use a chain rule in this method right here. I use the chain rule in this way of how I solve my problem, in this solution of mine. So let's recognize what's there, what I use there, so that it can be called a chain rule. Okay, so let me underline a couple of things. Now, I purposely left the 2 work here so that you can recognize one thing. In both partial derivative of f in respect to s or partial derivative of f in respect to t, we both have this following common thing. There's a y and a y in the first term. I want you to recognize that. There's an x and there's an x in the first term. And then there's a 1. Well, it's 1 times 0, but at least it's 1 times something, and 1 times a 2t here. But these components that I specifically underline in red ink right there, they have some meaning. There are some meaning. All right, so let's dive in even further. Okay, so think about our function from the beginning. I'm too lazy to swing back and forth between the 2 boards right there. I don't want to waste anyone's time viewing it by seeing me switch back and forth. So I'm just rewriting the original function here in terms of x, y, and z. So x, y plus z, that's my original function. So what is this? How is that lone variable here related to the beginning function? What I recognize here is that, hey, wait a minute, this is simply just df dx right there, df dx, because right here if you take partial derivative of f in respect to x, we're looking at just y. All of your skills in finding partial derivative must be brought in this particular problem right here. All right, so I recognize that first part in a product is that. So now what about the 2s right here that I'm underlining with the swiggling black line right here? Well, 2s. X itself was defined as s squared. So if I'm treating x here as a function of s and t right here, a function of s and t, then this is really, see, dx ds, the partial derivative. I mean dx ds. Okay. I should have written xs equals 2s, and that's what explains for this 2s right here. So in other words, this is going to be dx ds. All right. And so now the underlining red component right here is immediately recognized in my final work right here, and allow me to erase this final answer right here because we already had the final answer. Okay, the final answer was s cubed plus 2t. Okay, but I want to point out now, so it's y here, the underlying part, the underlying factor in this first product, it's really df dx. Okay, and then so now in my next one right here, x right here, this component, this x right here that I underline with red ink right there, I recognize that as my original function is here. So fy, think about if we took the partial derivative in respect to y right here, the first term becomes x. That last term is 0. So that's what it is. So partial derivative of f in respect to y. Okay, and then so multiply with t. So t here, our function for y. See, now we're looking at the y right here. We're dealing with the y. So y by itself, sort of like, so y is the outer, for now, for this specific term right here, we think about y as the outer function, and then t, I mean, we're looking at s as the inner function. So, but y is s times t. So ys equals just simply t. So this is d, dy, ds. Okay, so s is the inner variable. X is the first outer, y is the second outer variable. Okay, so here, same way how I recognize this, plus this x that I underlined, that was df dy. Okay, and then last one right here. Right, so last one right here, I'm looking at this. That component I underline. Okay, so think about if we are getting right from our beginning function, if we're getting f of z right here, f sub z, then that gives me just simply, that term is gone, that's just 1. That's how I get that. All right, so partial derivative of f in respect to z, but then I need to multiply with, let's try to have some explanation what that 0 represents. So z is a function of s and t, but it's only t squared. So taking the derivative of this in respect to t, see, zs in respect to s, that gives me a 0. So this is d z d ds. All right. And so similarly, now you can apply that understanding, and you can find it out here. This one that I underlined with red ink, yes, it's the df dz. Okay, and then let's find out what these other components are. That 0 here, okay, it came out from, this was dx, but this time, see, we're looking for a partial derivative in respect to t, so this is dx dt this time. Okay, and now, yes, df dy, but now we want partial derivative in respect to t, so down here it's dy dt. Okay, and then the last one here, the 2t here really came from dz dt. All right. So now I wrote down the work. We got the final answer. I wrote down the work, but then I want to make everyone to realize that inside of this work, the rule we're doing here is called the chain rule. Okay. So coming back to this board right here. All right. So x was a function further in terms of s and t. Y was a function further in terms of s and t, and that was s times t, and z was was another function, also in terms of s and t. Okay. And so what I did there, summarizing the work I've done, I recognize the chain rule as following. So this is the chain rule that I found for this particular problem. Okay. df, ds, the first final variable over here, the partial derivative of the function, of the overall function, in respect to the first final. This is sort of like the beginning, the initial level of variable, and then s and t are the final variables, the final level of variables. So the partial derivative in respect to the first, in respect to the first final variable. This is how we get in that, according to the work I recognize, like that. It's df dx. So we have to go through, so the x variable here is being regarded as the outer variable. Okay, and then we multiply with the derivative of the inner variable, dx, ds, like that. Okay, and then our beginning function, our main function didn't only have x as the only variable, it got y and z, so that's why we added. The next term now is df dy. Okay, so y is the next outer, the second outer the variable. Okay, so we multiply with dy ds. Okay, and then plus df dz, the third outer variable. We're going to multiply with the derivative of the inside, d dz ds, right there. So that's the chain rule that existed for df ds, the partial derivative df ds, in our problem that we've done earlier. And then we came over to df dt. So we did the same thing. Okay, df dx, but multiply with the inside derivative dx dt. So the dt here matching with that. All right, and then move on to the next variable, the next main variable, df dy. But df dy need to be multiplied with dy dt. All right, and then plus df dz multiply with dz dt. All right, so really it's one chain rule, but it can give you as many partial derivatives as you can. Okay, but that's what chain rule is all about. So we have recognized a chain rule that was existing directly in this particular example over here. All right, so this is about the end of the demonstration example, and then we already recognized the chain rule. So let's summarize that into a formal, the written statement of the chain rule. Okay. All right, so now I am going to write down the generalization of the chain rule. All right, so let's look at the formal generalization of the chain rule right here. Okay, so let's say for this general version of the chain rule, this generalization of the chain rule, we can go with, it's not only limited to 2 variables or 3 variables. It's applicable to as many variables as possible. So now I'm gonna do the following. That's a little bit unlike many other times I write function, multivariable function in other definitions. But I'm gonna say let's have a function of some n variables, x1, x2, x3 up to xn. This is a function of n variables. Okay, be an n variable. Okay. A function of n variables. That's why my shorthand notation n var. Okay, n variables function. So if we have that, but then aside from that, each variable here, okay, successively, or each variable here is going to have on its own each x of I over here. See, if we pick any index variable over here, each x of I is a function So each one of the variables x1, x2, x3 to xn is a function that I call, see, each one of them is an x of I as a function of some other variable. Let's name that. Let's name the other variable t1, t2, t3, and being as many as some m variables. Okay. So m variable function, and m could equal to n. Okay, the same number of variables in each level right there. All right, and so now as a generality, the chain rule says as following. So think about it. If we have a function of n variables in the beginning, but each one of these is a function of m variables, then ultimately we're going to end up with a final function of m variables, t1, t2, t3, up to tm. That's the idea. Just like if you're making that connection to the demonstration problem I showed earlier, then the beginning function really had 3 variables, but then each of the variables is a function of 2 variables. So our final ultimate function is only, our final function was only 2 variables. Okay, so just like that, if our beginning function really had n variables, but each of the variables here is a function of m variables, then the final function is only of m variables. But then, so in the end, we're going to have, for each partial derivative, okay, in respect to the inner, these are, I call the inner variables. Okay, for each partial derivative in respect to an inner variable dt sub k, then here's how we can do it. Okay, it's going to be df over dx1, the first, I mean the outer level, but the first variable multiply with dx1 dt sub k, okay, plus, and then df of dx2 times dx2 over dt sub k, okay, because it's all about the dt sub k, the partial derivative in respect to the kth variable, the kth final variable. K could be 3, could be m, could be whatever, okay, but they're all, see the second one, the second factor in each product here is in respect to the kth variable, okay, the kth inner variable, okay, and plus, so on and so on, up to the last one here is df dxn right here. So there should be n terms, okay, but multiply with dxn over dtk. All right, so that's a generalization, and with this one generalization, you can find as many partial derivatives as you can find as many as m partial derivatives for one function as like that, as written like that. All right. Okay, and so right at this point right here, then anyone viewing this lesson should be ready to view some examples. Can be either delivered throughout my video lesson here or directly in class if you're meeting with me face-to-face in class, aside from just watching through the video lessons here. Okay. All right, and so this next piece of information, very small piece of information, is really not too critical, but it's very beneficial to understand. So think about the definition I wrote down. Think about the rule, the chain rule I wrote down earlier. Okay, this rule right here. This rule may become a little hard to remember sometimes. So a lot of times you think about the demonstration example that I brought up earlier so that it clicks better with the rules. Otherwise, trying to crank through and memorizing this formula is a little hard. So in case that you have learned about gradients prior to learning about this video lessons about the chain rule, okay, so I'm repeating myself. In case you already learned gradient before learning about the chain rule, then you can recognize, okay, so you can recognize the following, and allow me to take away your viewing time a little bit by rewriting the formula here. Okay, it's df dx1 times dx1 dtk. df dxn times dxn dtk. Okay, so as I admitted earlier, I need to take some more of your viewing time right here, but I want to show you right from this right here, we can optionally, and I'm saying optionally simply because if you're learning about the chain rule after you have seen, after you have learned about the gradient, which is not always a strict required order, okay? Sometimes some instructor teach the chain rule before teaching about the gradient. So in case you already learned about the gradient before this point, then you can think of this as, you can treat this as a dot product, okay? You can treat this as a dot product between some two vectors. So the two vectors are as following, okay? So one partial derivative, I'm talking about finding one partial derivative, can be seen as the following. You see all of these, I can categorize all of these first components here in each of the product as the components of one vector. So what are there? df, dx1, okay, comma df, dx2, comma df, dx3, etc., up to df, dxn. That's one vector. And then we're in dot product with the other components being, okay, dx1, dtk, okay, dx2, dtk, okay, dx3, dtk, etc., and then dxn over dtk in a dot product with that. Okay, so this is dxn over dtk, and I understand that my board is getting a little tight with that divider right here, so it's hard to read, but dxn over dtk, and it's another vector. And so I mentioned about gradient because, hey, wait a minute, this first vector right here, this first vector is the gradient vector of the function f, okay? And then in dot products with, so now I have more space to write with the other vector being dx1 over dtk, okay, dx2 over dtk, comma dx3 over dtk, okay, etc., dxn over dtk. All right. So this quick little recognition right here may help it better to remember how we operate with a chain rule. Okay, by anytime that you would like to apply the chain rule to find partial derivative. Okay, but you are not really required to remember this formula. It's just something that we recognize right out of our fundamental formula for the chain rule. Okay. All right, and so aside from doing the usual examples about how we apply directly the chain rule to solve problems where a function of some number of variables, and each of the variables being individually functions of some other number of variables, aside of doing as examples those other direct problems, right? Now, chain rule that we just now learned has a very direct application. I mean, pretty direct, but very useful. So we're going to directly apply the understanding of chain rule into the following kind of problem right here, and it becomes a famous technique. Okay? And you have seen this technique since long ago, but now we're going to come up with the more generalized version. Implicit differentiation. All right, so that's why we can only learn about implicit differentiation after you have learned about the chain rule. And so now I do expect that this level of learning about the implicit differentiation is the much more advanced version of the implicit differentiation compared to what you've learned back in Calculus 1. However, this is also the most generalized version of that. Okay, so let me bring up the idea as following. All right, so if you recall from your Calc 1, bring in your Calc 1 a little bit, the days that you first learned about taking the derivative on single variable functions, right? Then a lot of times we were able to find, let's say when we were back in our days finding just straight old dy dx, right? Then we try to find things out of like an x squared plus a y squared equals a 5 or something like that. So what we have here is it's an equation, right? What we have here is an equation, and most importantly, if I'm asked to find dy dx, then that means y is implicitly, okay? Y is defined implicitly a function of x. And then similarly, you may also be asked to find, if you are asked to find, because same equation, they can switch role. Y can be implicitly defined as a function of x, but the other way around may also work. We can also be asked to find the dx dy, where this means x is implicitly, okay, it's implicitly a function of the variable y. And the term implicit, I really gave a very detailed talk in my video lessons when I was teaching Calc 1. Okay, so when anyone arrived here should be, and if you didn't even take Calc 1 with me, your professor back at Calc 1 should have explained clearly what implicitly defining a function means. Okay, and so now, so just like that, and I don't want to go back to ultra basic stuff with implicit differentiation from Calc 1. But let's take that idea, that similar idea exists right here in our function, our multivariable function. And so now, let me bring in the following. A lot of times we are given the following. Let's say the x, y squared plus z squared y, okay, equals x cubed, something like that. This equation has 3 variables involved. Okay? Or even more. Some equation got even 4 variables involved. The idea now is that we can pick one variable and choose that as a function implicitly defined in terms of the other one. So traditionally we target z, okay? But that's just a choice. Any of the variables here can be a function implicitly defined in terms of the other one. So what I mean is z can be a function implicitly defined in terms of as a function in terms of x, y, okay? The other 2 remain variables. Or y can be a function implicitly. So this is all implicit because it didn't say what that function is. Implicitly, okay? And the same thing right here. Y could be a function in terms of x, and z defined implicitly. Okay, and similar, and so on. And x can also be defined as a function in terms of y and z implicitly. Okay. So be prepared that your equation may have even 4 variables, 5 variables. You can always have a choice that there's always, be ready that any of the variables there can be implicitly defined as a function in terms of the remaining variables. That's what I've been trying to describe up here. Okay, but now I'm going to leave this demonstration example. The idea now, let's just pick one scenario. Traditionally, we stay with z being in terms of x and y. Okay, but like I said, what you learn here can be extended to the other cases. If that's so, if z is a function implicitly defined in terms of x and y, the number one thing we do is as following. We turn this equation into, okay, see, I'm going to completely bring all terms to one side. So in that way, subtracting the x cubed from both sides, I'm bringing that x cubed to the other side. I have xy squared plus z squared y minus x cubed equals 0. So the starting point is here. I recognize on that left-hand side now it's not the same as this implicit function, lowercase f. Here I see the whole left-hand side expression as a function of 3 variables. Okay, it's a function of 3 variables. And generally it's equals 0. My point is that, so now if you have an equation of 3 variables, you can purposely bring all terms into one side, making that a function of 3 variables, and everything equals to a 0 on the right-hand side. That's an equation. But on the left-hand side, you are expressing the left-hand side as a function of 3 variables. Our equations of 2 variables I brought up earlier. Okay, you can bring all non-zero terms, all terms to one side to become a function of 2 variables and equals 0. And then if you have an equation of 4 variables, okay, then you can bring all terms to one side, making it a function of 4 variables and equals 0. All right. And so now in that way, once you see the generality right there, allow me to just focus on this case of 3 variables, a decent number of variables, enough to make the work fascinating. Okay, so now I'm going to even erase out this this specific demonstration example right here. And I've left this title long enough. So now I'm going to start as a general algorithm right here for implicit differentiation. Let capital F of x, y, and z, okay, equal 0, be an equation, okay. I may word it slightly different from the way many textbooks are stating it. So I see this as an equation, but yes, it's in the form of one side being a function and the other side is strictly equal to 0. It's an equation, but 3 variables involved. And we put everything on the left-hand side as one function, capital F of x, y, and z. Okay, be an equation. And further, let's stick with the case and let's just suppose, right? Let's just suppose that, and suppose the z variable that we just target, it's just one choice that I pick. Even though, like I have explained earlier, it could be y as an implicit function of x and z, or x as an implicit function of y and z right there. So here I picked z because it's just quite traditional. So z is a function of 2 variables, x comma y. Okay, let's keep it that way. Let's keep it that way. So now the goal here, the goal is, if this was an equation, we want to be able to find the following. We want to find d, because it's really z is being regarded implicitly as a function in terms of x and y. So the goal is to find the partial derivative of z in terms of x and partial derivative of z in respect to y. So if z is an implicit function in terms of x and y, then there are only 2 partial derivatives that we can pull out of z. Okay, so in that way, here's how I'm seeing it. I'm going to use the other side of the board, but before I get there, we can write a little bit here. Right from this is our start. Here's how I'm starting to find these 2 right here. We're starting with our equation, because we want to get these, I have to note, this is only implicit. Implicitly, that means you don't even have to bother knowing what expression that is. Is that a z equals x squared plus y squared? We don't need to know that. That's why it's implicitly. Okay? So right from this equation, at that starting point, to find dz, dx, I am going to take the derivative, okay, of both sides in respect to x, okay. That's my starting point. Very similar to the days the days that any one of you learned about how you do the beginning implicit differentiation. Okay, so what can we do with this after that step? All right, so right from that point right here, okay, we want to differentiate, we want to take the derivative on the left hand side here in respect to x, because our goal is to find the partial derivative in respect to x right here, the partial derivative of z in respect to x. But we just brutally take the partial derivative on both sides here in respect to x, and then the right hand side is of course a 0. Okay, is of course a 0. All right, and then I'm going to leave that gigantic space right here to write my other work. But now think about it. This is just little scratch work right here. if f of x, if capital F is a function of x, y, and z, so now this is why I was saying this earlier, implicit differentiation that we're learning right now is a direct application of after learning the chain rule. So this is how I'm seeing it. X implicitly, or x inside of x, it's some function. It's just x itself. Y, and what I mean is really x is a function of xy. Okay? Y is a function of xy. And z is a function of xy. And so now I can treat xy as the sub-level of variables. That's the idea. Okay, so now by doing that, I'm going to apply the chain rule as following. Okay, so on the left-hand side, taking the derivative, okay, we're looking at d, capital F, dx, but multiply with dx, dx. Because see, the function, the capital F function has 3 variables, and taking the derivative in respect to x, but x is also a further sub-level, so I'm doing this partial derivative df dx times dx dx. And the chain rule says I need to do df dy, okay, but multiply with d dy dx. Okay. And the last one here is df dz. So these x, y, and z here, they are the first level, right? The outer level of the variables, the outer level variables, and then these x and y here, they are the inner level variables. Okay, so now that multiply with d dz dx. All right, and so far I'm trying to obtain this dz dx right there. Okay, and so that's my starting point. And so now, if you're looking at this a little more closely, this will be equal to 1. So in my next step right here, we're just simply having df dx, okay, times 1, plus, because that's 1, okay, plus, and then all of that here, this will equal to 0. Why is that? Well, y is a function of x and y, but honestly, on its own, it's y equals y. Where's the other x variable? We don't see it. So differentiating y here in terms of x means this is in respect to x, then this is only a constant term. So it leads to dy dx here being a 0, because there's no x present in this expression. Okay, whereas why did this become 1? Because x equals x. Okay, even though, so being treating that as a function of 2 variables, x and y involved, then partial derivative of this x in terms of x, that equals 1. Okay, simple logic, but sometimes they're hidden. Okay, and so now coming back to this, that term is 0, so I don't need to worry about that. I can see this as df dz, okay, multiply with d dz dx. Nothing much I can do about that. But now this one here is, and all of that equal to 0. So I'm about to solve for that one. This is the implicit differentiation technique right here. So dz dx, okay, can equal minus df dx over df dz. Okay, that's the short version. Or you can write it, you can write it in the shorter version, dz dx that we found right here equals minus capital F sub x over capital F sub z. Okay, we have found one partial derivative, okay, using implicit differentiation. And really, we didn't even have a specific equation, but this is, I can work completely just fine using the chain rule here, completely without knowing the equation, what it is, and it worked, okay? And so we came to a generalization that right out of an equation being expressed in that form right there, okay? And then if we keep z as a function in terms of x and y, then we can find the partial derivative implicitly, okay? The partial derivative of z in terms of x implicitly by going through that work, and we ended up with this. All right. So we're not done. We're only halfway, because the goal of this activity is to find the dz dy as well. We found dz dx, one of the partial derivatives. Okay. So if you need time to write down the formula here, feel free to pause the video. Okay. And otherwise, if you've had enough time writing it down, I'm going to go ahead and advance. Okay. So I'm going to come back to the other board. And now we're going to target the other one. All right. So there, I don't need to erase everything completely, because a lot of these can be kept here on the board. So now my focus is on finding dz dy. Okay, that's my focus right there. So I don't need to really erase everything and rewrite everything from scratch. From that equation, I'm going to differentiate both sides. From that equation, I'm going to differentiate. I'm going to differentiate both sides in respect to y. That's simply it. Okay. So it's pretty much very similar to how I moved the earlier work. All right. So now I'm really going to advance to my other board, and this time I can start picking up the pace a little bit. All right. So right from the equation of the last step, of the previous step, equals 0 on the right hand side is of course a must. Okay. Now on the left hand side, this is what we're going to have. Chain rule again. D f d x, but multiply with dx dy. Okay. Plus now df dy multiply with dy dy. Okay, and plus with the last one, df dz multiply with dz dy. Okay, and notice this is our target expression, partial derivative expression that we are desiring for. So just like that, this will be 1. Okay, and very similar explanation. Maybe I can throw it in one more time here. Y is supposedly a function of x and y, but it's really y equals y. That's ridiculously simple. So that means dy equals 1. That's why we have that. And then x supposedly equals a function of x comma y, but that function there is just equals x. X equals x. And so finding the partial derivative of x in respect to y really forces us to treat x here only as a constant, because the variable y is not present in this function right here. So that means this derivative is 0. Okay, and so in that way, that term is 0 out. In my next step, I have the following: df dy times 1 plus df dz times dz dy equals 0. And so yes, this is our goal right here. We want to solve for that. And so now I'm looking at dz dy, rearranging this equation algebraically. I'm looking at minus df dy over df dz. All right, that's a formula for finding dy dz, dz dy. Or in a shorter version, partial derivative of z in respect to y equals to minus fy over fz. Fy over fz. Okay? Two versions, whichever version that you prefer to work with, to write with. All right. Okay, so putting it together, then really, if your equation start out, if your equation is an equation in terms of three variables, right? Okay, and if z is a function implicitly defined in terms of x and y, then now what we have found earlier, dz dx, okay, we found earlier now as a formula, minus minus fx over fz. And I will come back and point out a good trick to remember, okay? And because we only have two final variables right here, so out of this equation there can only be two partial derivatives involved, okay, that we can find implicitly. And so the other one was dz dy, and we can find that by minus fy over fz. Okay, so that's another formula. All right, so at this point, anyone viewing the lesson here is ready for doing one example. I'm bringing in this example so that it can strengthen your skill right here. Okay, so the example says let's calculate dz dx and dz dy at the given triplets 1 1 1, which is basically a point, okay, where we have x squared plus y squared as an equation equals 2z squared minus 12x plus 8z plus 4. Okay, that's what it is for our example. So now I want to show the steps here of how easy that is, especially now at this point we have the formula. So I brought in this example so that it shows that I am not expecting anyone to go through the entire implicit differentiation deriving process right here, but we can just stick right here with the two formulas to show how useful the two formulas is. So the first big step is to bring all terms of this equation to one side. So now I'm looking at x squared plus y squared minus 2z squared, okay, plus 12x minus 8z minus 4 equals 0. All right, and so just like that, this entire left-hand side is going to be seen as my function, a capital function f of three variables, x, y, and z. There are three variables involved. Okay, so all that here, yes, let's make a note of that. All that here is our capital F of x, y, and z. Okay, so I'm going to move on to the other board and write down the capital F of x, y, and z specifically. And so now, f of x, y, and z was recognized to be from the earlier step. X squared plus y squared minus 2z squared plus 12x minus 8z minus 4. Okay, and that's capital F of x. Capital F of x, y, and z. So now, to find our dz dx as required by the problem, the formula says we just go one more time. Let's look back at the formula. The formula right here says we need minus fx over fz. Pretty straightforward. So we need minus fx over fz. So now I'm going to start saying it a little bit about the trick I said earlier, that I promised earlier that I would show anyone to remember this formula easily. You see, our function in this partial derivative that we are required to do, then the z here is the implicit function, and the x here is the implicit internal variable. Okay, so the fz in the denominator is corresponding with the, so it's the z here, the implicit function is always going to be put in the denominator. The partial derivative of the capital F in respect to the implicit variable, implicit function, is always put in the denominator. And then that x right here is corresponding with that x here. Okay, and so now anyone learning in this lesson is mature enough in math so that I can just, you know, do a quick work here in finding these partial derivatives. Fx here with the minus sign is going to give me 2x for that first term, 0 for that, 0 for this, plus 12. Okay, and everything else is 0. Okay, and then f sub z is going to be minus 4z, okay, minus 8. And then so we have our choice of canceling out the common factor of 2 and together with the minus sign, so we're ending up with x plus 6 over 2z plus 4. Okay, x plus 6 over 2z plus 4. Okay, and then we can advance to the next partial derivative, dz dy. So now I'm going to one more time strengthen the trick I mentioned earlier. See, the target, our implicit function that we're targeting at is the z. So we always going to put fz in the denominator. Okay, that's something worth to pay attention to. All right, and then now the corresponding, the variable, we are differentiating this z in respect to the variable y. So we're going to need to find a capital f sub y corresponding to that y variable. Okay, z is the function, y is the variable. So z is the function, y is the variable. It's going a little backward right there, but with the minus sign here. Always there's a minus sign. Okay, and so now in this way, with this formula that we are having here, and again, I'm going to speed up the process a little bit. Okay, so f sub z, we have found out previously from the earlier work. It's the exact same thing. So minus 4z minus 8. Okay, now f sub y with the minus sign, I'm putting the minus here. Okay, f sub y, okay, that gives me a 2y, and everything else is going to go to 0. So that's all we have. So really, it's going to give me the minus sign canceled out with the 2 minus signs here, and then common factor 2 will cancel with these common factors 2. So we're looking at positive y, or it's just simply y over 2z plus 4. We found the two partial derivatives. Okay, and so now the next step is easy. The problem is just asking us to evaluate these two found partial derivatives at this particular point right here, at this point 1, 1, 1. So we're just going to substitute this point, this triplet of values into the two partial derivatives, x for x, y for y, and z for z. Okay. And so I'm running short at board space right here, so allow me to do some short version of that. But the partial derivative dz dx here evaluated at 1, 1, 1. Okay, so I am going to skip showing the calculation step. Okay, it's going to be just, you see, we substitute 1, 1, 1 into this expression. And so 1 for x, 1 substituted for x, 1 is substituted for z. And so now we're looking at 7, 1 plus 6 is 7, okay? And 1 times 2 plus 4, so that's making it 6. Okay? 7, 6 is our answer for this. And then we're doing the same thing right here for the other partial derivative. The partial derivative of z in respect to y, but evaluated at 1, 1, 1. Okay, this value will come out being, okay, and again, I'm skipping the step where I show the calculations, but substituting 1 here for y and 1 for z, we got the denominator 6 again. Okay, it's just 1, 6 this time. That's our final answer. Okay, so this example shows anyone viewing the lesson how convenient it is once we have arrived at the two formulas here. Okay. But so now, aside from using the formula here for doing an example as what I brought in earlier, I would like to make a further generalization that even enhance your understanding, that strengthen your understanding in terms of implicit differentiation. So let's focus to the two formulas that I have given up here again. So as I explained earlier throughout the example, the good trick to remember is that, see, out of this equation with 3 variables, and for now we chose, and now keep in mind, I have to emphasize this, z being a function implicitly defined as a function in terms of x and y is just a choice, okay? That is a choice. And so once we have made that choice, then following along with that choice, then yes, we can find dz dx and dz dy, partial derivative of z in respect to x, partial derivative of z in respect to y. And then in that way, along with my explanation earlier throughout the example, then you see we will permanently put the partial derivative of this capital F in respect to z, in respect to the implicit, the generalization I would like to make here is that the variable that represents the implicit function is all, when we take that partial derivative, okay, when we take that partial derivative from the capital of F function, we're always going to put that partial derivative in the denominator. Okay, the partial derivative in respect to the whichever the variable playing in the role of the implicit function. The implicit function here is a z, so we put that partial derivative in the denominator. And then, so the other, see, this is now fx, right? The partial derivative of f in respect to the variable that's currently acting as the variable, we put that on top with a minus sign, just like that. So it's corresponding to, see, capital Fy here is corresponding to that y like that. And it's, yes, the order goes a little backward. The math led us to putting that variable here in the denominator and putting the other variable on the top. It goes a little bit opposite order. But so now, taking from that advice there, I'm going to pick a different scenario. Same equation. And of course, the skill you're learning here should be applicable to 4 variables, 5 variables, and variables. Okay? So the idea is we pick one among the variables here being the implicit functions in terms of the other remaining variables. So right here in this case right here, what if, okay, let me point out a what if right here. What if we choose y here as a function of the other 2 variables, z and x. That could be a choice. That could have been a choice. So in that way right here, then yes, we can find 2 partial derivatives, d, dy, so, but now y is the implicit function, okay? So dy, dx, and then corresponding, we can find dy, dz right here, okay? So in that way, so now easiest to remember, this time, the one that goes in the denominator has to be capital F sub what? Sub y right here, because it's corresponding to the variable being in the role of the implicit function. Okay, you see how, I hope at this point you're starting to catch what I'm explaining about how easy that is to understand these formulas. And then we always put the minus on top, and then now it's going to be capital F, okay, but the letter here should be corresponding to that remaining one, x here, okay. Now capital F, the variable here, that's z. That's how easy it is to apply the formula in many different situations, because that's implicit differentiation. This is not only the only case. This is not the only case. We can have the other cases. All right. So now that's one thing about, that's one generalization about the implicit differentiation regarding the formulas. But that's not all of the generalization I would like to make. Let me now point out another generalization that's quite useful for your understanding, for your mathematical understanding. Okay, so, all right, so think about, recall from your days doing implicit differentiations from in count 1 course where you were only focusing to single variable functions. So your equation back there, your equation that came out for implicit differentiation was a function of 2 variables and equals 0. Okay, a function of 2 variables and equals 0. And so right from that we have 2 choices, right? Because back in the days of doing count 1, we can do the, say for example, I point this out earlier, x squared plus y squared equals 5, for example, and we put all terms to one side, making it a function of 2 variables and equals 0 here. Okay, but so now in this equation here, if we choose y to be the function of x, then ridiculously it's just the function of 1 variable. Then yes, we were asked to find dy dx, and now since it's just a function of 1 variable, then there's no need to write the derivative, the partial derivative notation. It's just the plain old derivative. And then there was another choice. At least if it was my class teaching count 1, I would emphasize clearly that when it comes to implicit differentiation, we can have dy dx or a dx dy. Okay, so if we made our choice of choosing x as the variable in terms of y, as a function, implicit function in terms of y, then we can find dx dy. Okay, so now the generalization I would like to make is that the method we just now learned fits perfectly into what you've learned from count 1, or in other words, the technique you've done in count 1 can be also, or the implicit differentiation you've learned back in count 1 can actually be generalized under this category as well, under these 2 formulas, under these formulas that we recognize today. So what is it here? This is now our capital F. Okay, the variable being in the role of the function is the y variable. So we need to throw the capital Fy in the denominator first. Okay, and then the remaining one is the real variable, the letter that represent the variable. Okay, we put f sub x here with a minus sign. That's how we use the formula here. Okay, into the kind of implicit differentiation problems that we done back in count 1. But this new method works too. Okay, so similarly, in this case right here, if we are required to find the x dy, okay, because we treated x as the implicit function in terms of y, then we can do the following. The letter x here is playing in the role of the implicit function. Okay, so I'm going to have to put fx in the denominator, and then minus capital Fy on top. And that's what it is. And so now you can quickly, or after the lesson is over, you can immediately verify me by pulling out any of the implicit differentiation problem back from count 1. Okay, and instead of going through, and doing both methods, doing the method you've learned back in count 1 and doing the method applying the 2 formulas we've learned just now today, okay, it will come to the exact same answer. And so at this point, this is about the end of our lesson here, and anyone at this point is ready to be given with any example so that it strengthens your skill of how you apply this method into finding different implicit differentiation. Okay.